All right, on these slides, we're going to look at some basic definitions for certain types of events. Independent events, overlapping events, mutually exclusive events, and some basic probability notation we'll use throughout this unit, as well as a couple of formulas or rules to calculate probabilities of compound events. Specifically, the addition rule and multiplication rule makes up a majority of the work for our content in Standard 12. Okay. So some probability vocabulary on the first slide. Trial, outcome, and sample space. A trial is the physical activity you're doing. Rolling a dice, drawing a card, flipping a coin. All those random events that we typically describe when we talk about probability. The trial is the physical action. The outcome is the result of the trial. So if I'm rolling a dice, what number did you roll? If I drew a card, what card did you pull? If I flip a coin, was it heads or tails? The outcome is the result of the trial. All possible outcomes is a set that we call the sample space. All possible outcomes to rolling a dice are what numbers? Play Monopoly, you roll a dice. What are the numbers on a dice? I would have rolled what? You roll a dice, what numbers are on a dice? That's the sample space. When you flip a coin, what's the sample space? 2. Because what are the two outcomes though? The sample space is just what possible results might you obtain. The set of all possible results.
So for the coin, would I say 2 or would I say heads?
There's 2 different elements in that set. They're both heads and tails. 2 is the cardinality made up of heads and tails. Some different sample spaces on the backboard here. We use kind of those common random events, so drawing a card. How many cards are in a deck? Standard deck, no jokers. How many cards are in a deck? 52. 52 weeks in a year, that's all I always remember. 52 weeks in a year, 52 cards in a deck. How many suits are in a deck? What are the different suits? They're on the backboard behind me here. Different suits are all what? The 4 different suits. There's 2 red, 2 black. The 2 black suits are spades and clubs. The 2 red suits are hearts and diamonds. If there's 4 suits in a deck of 52 cards, how many cards are there per suit? There's 10 ranked cards, ace through 10, and 3 face cards. Face cards are the king, queen, and jack. When I roll 2 dice and take the sum, like if you were playing a board game, when I roll 2 dice and take the sum, here's a diagram that's helpful to talk about all the possible different outcomes for rolling a pair of dice. If I roll a 5 and a 3, their sum is 8. If I roll a 6 and a 3, their sum is 9. What's the most likely outcome when you roll 2 dice? What's the most occurrent possibility? What number is in that chart more than any other? There's only 5 aces. So there are 6 different 7s as I go on this secondary diagonal from bottom left to top right. You go to Prairie Meadows and play craps. 7's a good number to roll. When you roll 2 dice, sometimes you might roll doubles. What does doubles mean? 2 of the same number, right? I roll a pair of 1s, a pair of 2s, a pair of 3s, and so on. That would be this main diagonal from top left to bottom right. 2 1s, 2 2s, 2 3s, 2 4s, and so on. I reference doubles, so doubles means 2 of the same. There's 6 different ways to roll doubles. 6 different ways to roll doubles. I'll leave those up there, but those are a couple of good sample spaces to keep in mind because we talk about rolling dice or flipping cards, whatever. Some laws of probability, some common notions about probability. This first one talks about law of large numbers. There's a difference between experimental probability and theoretical probability. Theoretical probability is like the true probability. Experimental probability is based on what you're actually doing, the results you're obtaining. If I flip a coin, what's the chance that I get heads?
50%.
50%. So does that mean if I flip a coin 10 times, I get exactly 5 heads? Why not? It's random, right?
Yeah.
I might get more heads than tails, or I might get less heads than tails, right? That's experimental probability. I might get more or less than 50% of my flips to be heads, just based on random chance. Now, in the long run, for more number of trials, the results should be closer to the expected value. Say I flip a coin not 10 times, but now 100 times. Wouldn't I have a greater chance of getting exactly 50 heads and 50 tails in the long run? That's what that means. Larger number of trials means that we're going to tend towards that expected result more and more. The more you do something, the more your results are going to mirror what should happen according to the law, according to the probability. Given a small sample size, like only flipping a coin 10 times, I might have more variability in the results, right? I might have like 8 heads as opposed to the 5 that I should have. Thanks, Beth. If you play baseball, you might go a week without a hit. But over the course of the season, doesn't it kind of work itself out? Law of large averages is a false belief. A law of large averages says that some particular outcomes are due because they haven't happened recently. Say you're flipping a coin and you get 5 heads in a row. Does that mean that the next flip is more than likely going to be tails because it hasn't happened recently? No, nothing's due. I'm not due to get a tail because I haven't gotten one recently. That doesn't make any sense.
There's anyone getting lunch in here, you guys can come grab it when you're ready.
You guys heard of the game called roulette?
Yeah.
Roulette is that spinning board game at Prairie Meadows at the casino. You roll a ball into the roulette wheel, and whatever number it lands on is the winner. Sometimes you might bet on black or red. Sometimes you might bet on a specific number. They're going to post the results on the roulette table of like the last 10 or so different outcomes. People at the casino might see that there were 5 or 6 different black spins in a row, so they should now have that red. Does that make any sense? If you got 5 or 6 blacks in a row, are you due for a red? Are you more likely to get red in the next spin than black? No. You're not due to get the next result because it hasn't happened in a while. That doesn't make sense. It's still the same outcome per trial, the same probability of that outcome per trial. Nothing is due. You're not due to get the heads just because you haven't flipped a coin and gotten heads in a while. You're not due to spin the roulette wheel and land on black just because you got a whole bunch of reds in a row. It's the same chance each and every single time. No outcome is due. I haven't gotten a speeding ticket in several years. Does that mean I'm going to get one on the way home tonight? Because I'm due for one? No, that doesn't make any sense. Just like if you got a speeding ticket, now you're not going to get one for a couple of weeks, you know? So now you can drive really fast. Nothing's due. Okay, on this next slide, some notation and define probabilities. I notate the probability of event A with this notation here. P of A symbolizes or notates the probability of event A. P of A represents the chance that event A occurs. Probability varies between 0 and 1. The probability of an event varies between 0 and 1. What does the probability of 0 mean?
0%.
So what does that mean?
It will never happen.
It's impossible. Probability of 1 or 100%. What does that mean?
Happens every time.
It's certain. The closer probability is to 1, the more likely it is. The closer probability is to 0, the less likely it is. We talk about sample space. For a given sample space, the probability of that sample space has to be 1. What's the probability of getting a head when you flip a coin? What's the probability of getting a tails when you flip a coin? So altogether, 100%.
Boom.
Every sample space has a probability of 100% because it's every possible outcome all grouped together. Talk about complementary events. A to the C is the complement or opposite of event A. Complementary events are just the opposite. The probability of the complement of A is 1 minus the probability of event A. This should make sense to you. The probability of an event plus the probability of its opposite has to add up to 1. Does that make sense? Here's the chance that one thing happens. Here's the chance that everything else happens as its opposite. Shouldn't that just account for 100% of all possible outcomes? So if I solve this formula for the complement, it should read the probability of the complement is 1 minus the probability of the original event. When I draw a card, what's the chance that you select a club for a deck of cards? What's the chance that you select a club for a deck of cards?
15,
Which is what proportion? What percent?
25.
25%. So if there's a 25% chance of drawing a club, isn't there a 75% chance of not drawing a club?
Yep.
Just the opposite. 100% minus 25% means 75% of doing the exact opposite of drawing a club.
Yes, sir.
I want to find the probability of the complement. It's just everything else. Right? Next several slides are on different types of events. I can have pairs of events fall into these different types of descriptions. Once again, these are up on the board too. Find you. Disjoint events are two different events that cannot occur simultaneously. Two different events that cannot happen at the same time. Is there any overlap in this Venn diagram between event A and event B? Do they share any outcomes? Is there any overlap? No, two separate sets, two separate circles in the Venn diagram. They are what are called mutually exclusive. Disjoint events, mutually exclusive events, those mean the same thing. You hear it both ways. Two events are disjoint or mutually exclusive if they share no common outcomes. They can't occur at the same time. I go back to the deck of cards. Could you draw a card that's an ace and a face card? Could you draw one card that's both an ace and a face card?
No.
Why not?
Because they're two different things.
They're two different things. They're mutually exclusive. There are no cards that are both aces and faces. They're disjoint or mutually exclusive.
Ace.
Ace and face. Ace, king, queen, jack. Overlapping events are just the opposite. Two events are overlapping if they share common outcomes, if they can happen at the same time. Overlapping events can occur simultaneously. This typically causes people the most problems because you don't want to double count what occurs twice. You don't want to double count the overlap. In purple, aren't these outcomes in both set A and set B at the same time? It's the overlap in the Venn diagram. Two events are overlapping if they can occur at the same time. Let me go back to that deck of cards. Aces and faces were disjoint. What would be a good example of overlapping events when it comes to the deck of cards? How about a black and a 10? Could I draw cards that are both black and 10? Because there are two cards that are both black and 10, the 10 of clubs and the 10 of spades. There are cards that are both black and 10. There's overlap. There are common outcomes between drawing a black card and drawing a 10. We had disjoint or mutually exclusive. We had overlapping. This last type of event is called independent events. A pair of independent events is where the outcome of one event has no impact on the outcome or chance of another event occurring. What you get on the second flip of a coin has no impact on what you got in the first flip, or is not affected by what you got on the first flip. Two events are independent if the fact that A occurs has no impact on the chance that B also occurs. What are some examples of independent events? Connor gave one. The chance that you get a heads on the second flip is not impacted or affected by whatever you got on the first flip, right? It's the same probability every single time. Other examples of independent events. Selecting a blue marble from a bag, pulling an ace from a deck of cards. Does choosing the blue marble affect the probability of getting the ace when you draw a deck of cards? No, they're two different things. That's ridiculous. That last bullet point. Why is this independent? Pulling a club from a deck of cards, replacing it or putting it back, followed by selecting a face card. Why are those two independent events?
Get the cards out.
So it's the same deck I pulled from the first time. By putting the card back, I'm drawing from the same deck, so it's not impacted by whatever I pulled out first, in this case, pulling the club. Last slide. We'll look at some examples. Last slide gives me two rules of probability we're going to study here in Standard 12. These are called the addition rules and multiplication rules. Let me also explain some notation here. For two events, A and B, the addition rule states that the probability of A union B, or in other words, A or B, this is set notation. This means union or, in other words. The probability that either A or B happens is equal to the probability of event A plus the probability of event B minus the probability of A intersect B, or A and B. This is set notation for and, or intersection. To find the probability of one or the other, you add them together, but then also subtract off the overlap. Subtract off what you would have double counted by adding event A and event B together. The multiplication rule states that the probability of A and B occurring at the same time. Multiplication rule means multiply. So I'm going to multiply the probability of A times the probability of B. This is set notation for intersection, or and. The probability of A and B occurring is the probability of one times the probability of another. All right, let's try some basic probabilities. We'll use cards. It's a nice random. Draw one card. Standard deck. Find the probability. We're going to be using the addition rule because I'm trying to find the probability of either selecting an ace or a 10. The probability rule says that the probability of drawing an ace or a 10 is the probability of drawing an ace plus the probability of drawing a 10 minus any overlap that would have occurred by adding up all the aces and 10 cards together. Are these two events mutually exclusive, or are they overlapping? Are there any cards that are both aces and 10s?
No.
No. So I'm not going to worry about selecting or subtracting the overlap. We'll do that here in the next example. How many cards in a deck are aces? 4. So the probability of pulling an ace is 4 out of 52. 4 of the 52 cards in the deck are aces. How many cards are 10s? 10s, there's 1 10 per every suit. So how many 10s altogether?
4.
There's 4 of every kind of card.
True.
4 out of 52 plus 4 out of 52 makes 8 out of 52. What does that reduce down to? 2 out of 13?
Yep.
So you can answer as a ratio, just make sure it's reduced. If you want to answer as a percent or decimal, that would be fine too. So if I grab a calculator and type in 2 out of 13, that's about 15.38%. .38%. Give it as a ratio, give it as a percent, doesn't really matter to me. Probably one to go. Probability of club or face.
Your face.
How many clubs are in the deck?
Thanks.
Add it with how many face cards are in the deck. Are face cards and club cards overlapping? Are there any club cards that are also face cards?
Yeah.
So I need to subtract those. Let me come back here. I'm going to underline all the clubs. All of the top row. How many cards did I just underline? 13. So 13 out of 52. How many face cards are in the deck? There's 3 per suit. Jack, Queen, King. 4 suits total. How many face cards are there?
12.
Wow.
It's cool, genius.
Now I've added up all the face card outcomes. Now what makes this different? Aren't there some cards that were counted twice?
Yeah.
I don't want to count something twice. I want all the unique possible outcomes. So what do I have to subtract off?
6.
How many club cards are also face cards? 3.
Oh.
What did I
It's not black.
What did I underline twice? What did I double count? Jack, Queen, King of clubs. These got counted as a part of the club set. These got counted again as a part of the face card set. Well, I don't want to double count them, so I have to subtract off 3 that I double counted as a part of each of the 2 events, clubs and faces that I added together earlier. 13 plus 12 is 25, minus 3 is 22. 25 out of 52 reduces down to 11/26. What is that as a?
You should
No, 42.31%. Let's try these. I'm going to put 2 up here on the board for you. Do those 2, please. I'll put the answers up in a minute. Oh, find each probability. Black or ace, heart or 2. You grab a deck, you pull 1 card. What's the probability of either a black or an ace? And number 3, or in the last one, what's the probability of either a heart or a 2? Add up all the black cards, add up all the ace cards, but then think about which cards you double counted that we have to subtract off for your final value. I don't want to double count things more than I should. How many black cards are there? 26. It's half the deck. All of the spades and all the clubs. 26 cards in total. Answer as a ratio or some decimal percent, doesn't matter to me. Make sure your final ratio is reduced down if that's the route you want to go.
They just dropped the sink in. He did all that. No, he told me to sort this class like draws. So dumb. Wouldn't there be?
I'm adding 26
Yeah, but
clubs, but then the other two aces that are also.
one will cheese. Wait, I thought, but you have to subtract some aces.
Okay, so there's 26 clubs.
Wait, no.
There's 4 aces, but I need to subtract off the 2 clubs.
No, what don't you understand? I do understand. No.
Let me do this here. Here's all the black cards. Here's all the aces.
Yeah.
So there's 13 plus 13 plus 2. 28 in total. 7 out of 13 is 53.85%.
I just thought there was 8 before. I thought this 8 was before. How's
Let's see, heart or 2, that's 13 plus 3.
Yep.
13 hearts plus the 3 twos that I haven't accounted for already. That's 15 out of 52.
16. 13 plus 3. Yeah, it's 16.
Oh, thank you, not 12. 16. There's 13 hearts, and there are 3 more twos I haven't accounted for already. Or you could do 13 plus 4 minus 1. 16 out of 52 reduces down to what? 4 out of 13. 4 as a decimal. 0.3077. What are your thoughts there, guys? Any problems with those 4? That makes sense. Why you have to double count what you. Why you have to subtract off what you double counted.
Yeah.
Okay. Don't want to count events more than once.
Wait,
Only want to get the possible outcomes.
Would we double count on this?
What do we double count on once? On the third one, we double counted the 2 black aces.
Yeah.
So it's 26 plus 4 minus 2 makes 28.
Yeah.
On the last one, we double counted the 2 of hearts. So it's 13 plus 4 minus 1, or 16. Could you get your laptops out and get on the screen? Let's talk about the rest of the week. Next week's November. That's nuts.
That is nuts.
We got an extra hour of sleep this weekend, too.
Yep.
We get stay up now.